stable, strong. These specially formulated racing tires have precise adhesive qualities and are the only way to connect 8,000 horsepower to the ground. Top fuel dragsters have about 43 times more power than an average passenger car and can accelerate from 0 to 100 miles per hour in less than 0.8 of a second. Only if the high-tech tires perform perfectly.
One of the most important things in racing is obviously rubber, and that's also one of the biggest secrets in racing because that's basically where most of your speed comes from.
Designed to stretch like a rubber band, these tires grow in diameter as centrifugal force increases.
As the tire is sitting static on the race car before he launches off the line, you'll probably have about this much sitting on the racetrack. As they go down track at, say, 250 miles an hour, the tire will actually stand up and act as an overdrive gear so that the race car can actually keep pulling as it goes down the racetrack.
We use our motorsports to advance our technology, and every car that races is really a moving laboratory.
Dragsters, sports cars, and stock cars provide valuable research to the manufacturers of the tires found on everyday cars and trucks. Tires are the most widespread use of rubber. Over 1.3 billion tires are made each year and account for 68% of all rubber production. In total, the world consumes 20 million tons of rubber annually. Some experts contend that rubber is the fourth most critical resource in the world, after air, water, and oil, and perhaps the most fragile.
Rubber, as we know it, and as it's grown in plantations, is Hevea brasiliensis. Hevea is a genus in the family Euphorbiaceae. The Euphorbiaceae family typically has latex in the various species. The latex is a protective mechanism against insect predation. Of course, the insects chew into the plant, and the latex, being a gummy substance, will clog up their mouth parts and protect the plant.
Found in rainforest regions around the equator, the delicate latex that oozes from beneath the bark is the base for rubber compounds.
The challenge comes, how do you get to the latex without cutting into the cambial layer of the plant, which is a living growth layer of the plant? If you cut too deeply in, you will actually hurt, if not destroy, the plant. And just by going into the bark layer, just into the latex vessels, you will get this sort of beautiful milk coming out, which is often called the white blood of the forest.
Latex extraction dates all the way back to 1600 BC and the Mesoamerican Olmec civilization, which loosely translates to rubber people. The Olmecs played a sophisticated game with a latex ball, made by dripping the gooey substance into boiling water.
They took the liquid that came from the hevea tree. They were able to let this dry, roll it into a ball, and then it would bounce. And so it was a great plaything at that particular time. And that's the only thing that people really knew about rubber, was that it was no particular economic value.
During the 16th century, Spanish and Portuguese conquerors of South America documented the many uses the indigenous tribes had developed for the white blood of the forest.
They found that they would coat their crude cloth with the same latex, and it become a waterproof covering. It was latex that was dried on cloth.
They made capes, they made rubber shoes, but all these products had a critical flaw. In hot weather, a rubber cape would become a sticky shroud, and in cold weather, a pair of rubber shoes would crack like porcelain.
Despite the shortcomings, the sailors coerced the natives to milk more trees as the wondrous latex started to be shipped to Europe regularly. However, the long passage would often result in spoilage and hardening of the product. Until 1761, when Dr. Francois Fresneau, a French scientist, discovered that turpentine was an ideal solvent for the crude latex and revived its pliable properties. This discovery opened the door to the global trade of raw rubber.
By the early 19th century, Europeans and Americans understood that rubber had a consumer use. And so there were a lot of sort of inventors and chemists who were trying to find a way to make rubber a more viable product for a wide variety of consumer goods.
Processing rubber began in earnest when Thomas Hancock built his masticator in 1819, which shredded scrap rubber like a meat grinder. Hancock learned that the mashing would warm the rubber into consistencies that could be shaped and would more easily mix with other materials. This process paved the way for improved quality products from men like Charles McIntosh, who in 1823 produced the first commercially viable raincoat, the Mac. But the most significant breakthrough in rubber processing came quite by accident to a man named Charles Goodyear.
It happened in the privacy of his own kitchen, and it happened under the conditions of a beleaguered husband who didn't want his wife to know that he was still trying to make rubber useful for humans, and somehow in the process accidentally made the right combinations of elements work. The accident happened in how much he heated up the rubber, and that's why vulcanization, Vulcan being the Roman god of fire, is the name of the process.
When Goodyear introduced sulfur under heat and pressure to natural rubber, it formed bridges between the strands of latex molecules and bonded them together in an unbreakable manner to give rubber its elastic properties.
It was only the accidental discovery of vulcanization by Charles Goodyear that transformed rubber from a curiosity to a fundamental component of the industrial age. And that was an extraordinary discovery, and the consequences were profound.
Vulcanized rubber for shoe soles, dolls and toys, bicycle and carriage tires, telegraph and electric cable insulation. At last, industry realized rubber had significant economic potential. Hoping to capitalize on the opportunities rubber offered, the British set out to grow rubber within their colonies. They dispatched Henry Wickham to disrupt the monopoly Brazil had on the valuable rubber resource.
The British managed to get some seeds out of Brazil and tried to propagate the hevea tree, and they managed to get some of those trees to germinate from the seeds that they took. And they started a rubber plantation business in Sri Lanka, or actually the island of Ceylon.
One of the things they discovered, for example, is that it was far more efficient, both in terms of productivity of latex and in terms of the speed of growth of a plantation, to propagate the trees vegetatively, not by seed, but from cuttings, from vegetative cuttings of the plant. Once the plantations came online, the reversal of fortunes was absolutely astonishing.
In time, these British-controlled plantations would become the primary suppliers of the world's rubber demands. But during the last half of the 19th century, the real rubber fortunes were found in the heart of the Brazilian jungle. Where the Negro and Amazon rivers meet lies the city of Manaus. A city of fantastic wealth and home to the plantation owners who controlled the world's rubber market. They became known as the rubber barons.
Manaus, which was the epicenter of the trade, had the highest per capita consumption of diamonds in the world, and prostitutes that came in from Marrakesh and Tangier and St. Petersburg would collect $7,000 to $8,000 for an evening's work. Men would slake the thirst of their horses with chilled French champagne. The matrons of the town of Manaus dispatched their laundry to Portugal because they disdained the murky waters of the Amazon. Now, all of this wealth was based on this tree of life, Hevea brasiliensis.
A tree of life to some, a tree of suffering and death to others. The arduous task of tapping the latex required an enormous labor force, one that was considered expendable by the landowners.
And when the supply of manpower from the impoverished northeast of Brazil became exhausted, the rubber barons in their greed turned to the first inhabitants of the Amazon, the Indians. It was one thing to sort of secure in a form of bondage, indentured labor, some impoverished peasant. You know, you would give him a certain amount of goods. He'd incur a certain level of debt from which he could never escape, a debt that would be inherited through the generations. That was one thing. But what about the Indians? How do you force them to work? Well, the rubber barons looked around for a reason, and they settled upon terror. And the atrocities that were unleashed at the height of the rubber boom are simply too dreadful and formidable to even begin to speak about them.
Little was ever said about these human tragedies. Outside the jungle, few were aware the plight of the natives was to be slave labor. Yet their sacrifices would facilitate the rapid expansion of rubber exports at the turn of the century. It was a time rife with invention, innovation, and imagination. It was the birth of a new industrial age and a time for a new means of transportation, the automobile, which would strain the world's rubber supply. The name rubber is credited to the noted scientist Joseph Priestley, who in 1770 discovered that dried latex rubbed out or erased pencil marks. Rubber will return on Modern Marvels. Engineers study tire performance characteristics to give today's vehicles maximum grip and durability. At the onset of the auto industry, makers of these newfangled contraptions struggled to obtain adequate performance from wagon or bicycle wheels. The solution was a rubber tire. Some visionaries were quick to seize the opportunity, and a handful became giants of the tire industry.
Dunlop is one of those. John Boyd Dunlop was an Irish veterinarian. He took a rubber tube and a valve from a football, and he wrapped this thing around the wooden wheels on his son's bike, and he pumped some air into it to make it more cushioned, and in the process invented the pneumatic tire. Like so many of these stories, a lot of this was just invention by necessity. B.F. Goodrich was a Civil War surgeon who, after the war, was looking for his niche in the business world. That he decided to establish his then fairly modest rubber company in Akron, and stuck it out long enough, struggling much of the time, for the automobile to enter the picture, which of course changed the entire industry. And one myth about the tire industry that's probably easy to understand is that Charles Goodyear started the Goodyear Tire and Rubber Company. But in fact, Frank and Charles Seiberling did start the Goodyear Tire and Rubber Company and named their company in honor of the man who had invented vulcanization that made their product possible. And the story of the O'Neill family's tire company, General Tire, is amazing in its own way, because they succeeded not only in making tires, but understanding that in this very young industry there were niches, and the niche that nobody had latched onto was replacement tires.
Some tire makers forged strong bonds with car makers.
Harvey Firestone was born a farm boy in Columbiana, Ohio, very rural part of the state. He sort of was often portrayed as this sort of pull yourself up by the bootstraps kind of guy who rose into this very blue blood, very regal figure. He struck up a friendship with a young man named Henry Ford, and in fact it was over the issue of tires. Harvey Firestone moved to Akron and started the Firestone Tire and Rubber Company. His early friendship with Henry Ford would come back to pay off in spades, because for years Firestone was the main supplier to the Ford Motor Company, and that was both a personal and professional relationship that carried really across the 20th century.
Ford and Firestone were intensely aware of how critical and how fragile rubber was as a natural resource. As World War I put an enormous strain on the world rubber supplies, Ford decided to protect his interests by establishing Fordlandia in 1926. His 2.5 million acre parcel of northern Brazil first had to be cleared and terraced. Then seeds from the hevea trees were planted across the valleys and hillsides. In just a few years, a thriving company town plantation supported thousands of workers. Beyond Ford's control, however, was the ever-present leaf blight, which decimated his fledgling crops. Fordlandia faltered and failed. So Ford created a second plantation, Belterra, in 1934. While it outperformed Fordlandia, it was still not successful. Better luck came to Ford's friend, Harvey Firestone, who focused his efforts toward a different area near the equator, on the continent of Africa.
Harvey Firestone
decided that he would make an agreement with Liberia and start a plantation to produce our own rubber, our own latex. That plantation is still in use today. At the height of its productivity, it had over 10,000 employees. As it sits right now, we have over 8,000 employees that harvest the natural latex rubber that's used in our tires today.
While plantations were located all along the equator, rubber production was dominated by those in Southeast Asia. But all were about to become pawns in a global game of military strategy. The sudden entry into World War II forced the U.S. government to set goals for rubber consumption that far exceeded natural rubber production.
Rubber was wrapped around every mile of wiring in every military and every domestic installation in this country. Every Sherman tank had half a ton of rubber. Every battleship that was to be sunk at Pearl Harbor had over 20,000 rubber parts.
After Pearl Harbor, the Japanese seized control of the massive rubber plantations in Southeast Asia, crippling the Allies' access to rubber supplies.
It was an incredible crisis. At that moment, 95% of the world's rubber supply grew within 15 degrees longitude and latitude of Singapore, the first place the Japanese planned to hit. The Japanese took the entire world's supply, leaving us without a vital commodity of the industrial age. Roosevelt set into motion 3 draconian initiatives that in wartime situation were became really the great symbols of the spirit of American industry. The first thing that we did is set in motion the biggest recycling campaign in the history of the earth.
Americans were asked to salvage and collect used rubber and a long list of other materials which could be repurposed for the war effort. These scrap drives were the subject of great publicity in the early days of the war, as a way for average citizens of all ages to support the country in its time of need. The second initiative required aid from citizens with expertise in natural resources.
We sent plant explorers to every corner of the free world to squeeze every drop of latex we possibly could. Above everything, we sent plant explorers back into the heart of the Amazon, not only to secure new sources of latex, but more importantly, to find a way to forever free ourselves of dependency on distant plantations.
But it was the third directive that made the most vital impact. A decree to manufacture artificial rubber.
The order went out to the synthetic chemists that they had no choice but to create an industry. They were told that if by 1943 you can't find a way to make 1 million metric tons of a product that has not even entered the developmental stages, the war will be lost.
So a real push was made to develop our own synthetic rubber. The government actually nationalized many of the plants and took over and set priorities for the development work. And we were successful in doing that.
The basic discoveries in the laboratory gave a good impetus to it, but it was the scale up to production quantities needed for the war effort that really became almost a miracle of the same order as the Manhattan Project. That is a government industry, university research combine that really pushed as hard as it could to get somewhere in a very short period of time, in the space of 2 years, producing hundreds of thousands of tons of a quite usable synthetic rubber. Quite important.
Synthetic rubber. The chemical manipulation of elements that produced a substance which emulated the properties of natural rubber. Experiments with synthetics predated the war by 2 decades. German and American scientists grappled with petroleum-based formulas to create Buna-N and neoprene. These early substitutes for rubber were precursors to the synthetic compounds that were directly responsible for meeting the military's demands. Those compounds provided the war machine the rubber resources needed to operate successfully. The complex process of creating synthetic rubber that was developed during World War II applied principles that are used in today's synthetic materials. Creating synthetic rubber is an art form rooted in elementary chemistry. Atoms group together to form molecules, and molecules are linked together to assemble strands of complex molecules, known as polymers. As more polymers are created, the massive strands entangle, much like spaghetti.
Through vulcanization, you can essentially connect all those individual molecules, practically making one giant molecule of rubber. And if you can think, if you let a plate of spaghetti sit, pretty much everywhere the spaghetti touches another strand of spaghetti, it's going to stick together.
Chemists blend carefully measured ingredients using precise recipes to create the exact consistency desired.
Yeah, we've got an example of a very simplistic formula for you just to demonstrate the different building blocks that go into a rubber compound. This is the raw synthetic polymer. This is actually EPDM. It's an ethylene propylene with a diene monomer. With this, we're going to incorporate some plasticizer. It's basically oil. It's a plasticizer that has a specific property that will extend and soften this batch. This is an example of the carbon black that's going into the batch. A very little bit of this goes a very long way. This is also one of the ingredients, a silicate, a clay-type material. This material is the curative. It's sulfur-based, but there's a number of the different colored materials in there are actually different chemicals. We got a little bit of Modern Marvels Custom Mix 101. We've taken the materials that we just described, and we're actually going to use a technique called upside down mixing, where we're going to load the carbon black, the balance of the fillers and plasticizer, and then load the polymer, the raw synthetic EPDM, last. Lower the RAM, masticate, put this together, and then based on temperature, we will add the curative to the mix to get a homogeneous mix.
Akin to making pie crust dough, all the ingredients for this exclusive recipe are mashed together and kneaded until pliable. Then the mixture drops down to a mill that compresses the rubber into a uniform consistency.
It's a little bit of a black art, even the way he's handling this.
The synthetic rubber compound then passes through a second mill, called a calender, which squishes the rubber to the desired thickness, then slices it to a prescribed width. Next, the strips are coated with a solution that will help prevent the rubber from sticking to itself. The final step for our Modern Marvels custom blended synthetic rubber is to drape it over cantilevers so it can cool and dry. Since World War II, the manufacturers of synthetic rubber have made great strides in polymer science. These advancements facilitated the production of an indispensable industrial creation, the tire. Wallace H. Carruthers, who headed the team at DuPont that formulated neoprene, is also credited with creating nylon. Rubber will return on Modern Marvels. The massive ramp-up of rubber production to support the military during World War II reached full speed thanks to the support of some muscular machines.
The rubber industry is the only industry in the world that has machines that are just over-designed and overbuilt, and they'll last a lifetime. We've had machines here that are over 100 years old, and we'll go ahead and put in new bearings, new gears, and a better drive, and send it out for another 100-year production.
At Rubber City Machine in Akron, Ohio, the vintage tools of the trade are restored to their optimal operating capacity.
This machine is a laboratory mill. By the design of the frames, I could tell that it was about 100 years old. This is a French oil mill press. It's made in Piqua, Ohio. Originally, this probably could be used for making hard rubber battery cases for automobiles and motorcycles. This vintage is about 1935, 1940. It looks really bad, but it'll go out looking like a new press. This is a two-roll mill. This is definitely a gem. It was built prior to 1900. We could regrind the rolls, put in new bronze bearings, new gears, of course, and rebuild this, put a new drive on it, and it would go out and last another 100 years.
The durability and brute strength of equipment like this helped make it possible to overcome wartime rubber shortages. But peace offered no slowdown in the production of natural and synthetic rubber.
The bottom line is the war was a driver for an awful lot of things in this country. The economy boomed after the war for many reasons, not the least of which was all those materials that were developed in support of that war machine were now able to be used by the consumer.
There was a demand for new products and labor-saving products, especially making the quality of life easier, less work for the household. We had the concept of the new family unit that was going to have a car, was going to have perhaps 2 cars.
And each new car was equipped with 5 new tires. The rapid rise in tire sales was good news for the small Midwestern town of Akron, Ohio.
As the tire industry sort of boomed with the rise of the automobile and building of more highways and all of that, most of the Akron rubber companies focused on tires as their main moneymaker.
Innovations in tire technology have always been the best way to bolster tire sales. The early balloon designs with an inner tube gave way to the tubeless style, with a new thin inner liner molded into the tire to retain the air and support the tire. This design was called bias ply tires because reinforced rubber belts were wrapped along the bias, or direction of travel, for strength. Then sidewall and tread layers were molded as exterior surfaces.
Bias tires, which were the typical construction feature up to the early 70s, were very fuel inefficient.
In 1948, efficiency was engineered into a radical new design, the radial tire.
The inventor of the radial tire, his name is Marius Mignot. And what's interesting is that Marius Mignot was hired into Michelin actually to work in the printing department. But Michelin gave him the opportunity to work in the area of tire design and tire engineering. And as a result of that, we have the radial tire.
The radial design featured reinforced belts that radiate in a circular pattern, 90 degrees perpendicular to the direction of travel. This configuration provided strength across the entire surface of the sidewalls and tread layer, and greatly improved efficiency. But the Akron tire makers were reluctant to accept the revolutionary design. For the next 20 years, they would mold innovative fabrics with rubber to enhance bias tires.
The first 50 years of the tire industry was about a bias configuration, cross-ply tire, that would last you 10 or 12,000 miles. As we moved into the 60s, we invented our polyglass tire, which was a reinforced tread area with fiberglass belts under the tread area, which raised the whole performance level to now you're talking 35, 40,000 miles was an expected life in a bias tire.
Not until the oil crisis of the 1970s and the demand for fuel-efficient automobiles did the tire makers adopt the radial tire, the design that changed tire construction for good.
The construction features of today's radial tire are a radial body ply, generally made out of polyester, a bead filler material, which allows us to adjust the stiffnesses of the sidewall of the tire, 2 steel belts in general. These steel belts are at a bias, they're on angles, opposite to each other, to give the tire the ability to generate cornering force, as well as a cap ply material and tread rubber that translate all of the behaviors of this structure to the road surface. The tread region, the tread rubber, is really where the technology advancements over the last several years have come from. And that's really from polymer evolution, from the ability to blend different synthetic rubbers with other naturally occurring materials to produce the overall performance of the tire.
Processing these high-tech, highly secret, and proprietary rubber compounds is done at state-of-the-art facilities, like the Michelin plant in Greenville, South Carolina.
Most of the rubber, the elastomer that we receive, comes either by rail cars, you see behind me here, or by truck, coming either from domestic production, or in the case of the natural rubber, coming largely from Singapore. Its natural color is a dark tan. Also, you'll notice the elastic properties. You see how stretchy it is, how soft it is. Those are part of the properties of natural rubber. And then on this table, we have examples of synthetic rubbers, synthetic elastomers. This one is styrene butadiene, which is mainly going to be used to improve traction. This one is polybutadiene, or PBR. It's going to be mainly used to improve rolling resistance. And this is yet another form of natural rubber, which would be used mainly to improve endurance. In this factory, we manufacture about 100 different recipes or formulas. And if you think about a tire, the properties that you need in the tread block of a tire are not at all the same as the properties you need in the inner liner or in the sidewall.
Chemicals and additives are precisely mixed with rubber to the specifications of a recipe.
These chemicals are weighed on the machine behind me to very precise weight tolerance. And just as an example, here you have an antioxidant which protects the tire from attack by oxidation. This is a resin. It helps it to adhere to the metal. This product is a wax that helps in the processing of the rubber and also helps the tire to stay black. This is another antioxidant. This product is an anti-ozonant, so same purpose except this time to shield the tire from attack by ozone. You would have anywhere from 3 to sometimes up to 8 of these different chemicals in a given formulation, but when you add it all together, it would only represent 3 or 4 total percent of the weight of the rubber compound.
Tons of natural rubber is chopped, tumbled, and washed as it makes its way across the massive plant toward the mixing machines and mills. After passing through the secondary mill and calendar, the compound is fully homogenized and identified with a recipe code. Once cooled, it is folded and palletized for transportation to the tire plant.
You know, the rubber industry is no longer the dirty, filthy industry that it used to be in the old days. In fact, you can see this is a very clean place to work. It's a very high-tech, high-automation industry.
The same is true for the tire manufacturing plants, where computers and robotic operations build radial tires from the inside out. Step by step, layer by layer, tires are assembled with a myriad of rubber compounds. Starting with the inner liner, the steel belted plies, sidewall supports, and bead wire. Then the assembly is automatically inflated so that a tread layer can be applied. Next, this uncured tire is placed in a mold where it is subjected to extreme heat and pressure to vulcanize all the elements. In the final production phase, each and every tire is quality controlled by technicians who must approve every aspect of the automated process. Random samples are frequently pulled from the line for spot inspection and testing. The basic process of mixing natural and synthetic rubber with other chemicals and additives into a pliable compound that can be molded, injected, compressed, or extruded isn't just used in making tires. It also creates many other products that surround us daily. There are approximately 165 pounds of rubber in the average passenger car. Rubber will return on Modern Marvels. The 1960s saw many new uses for rubber. In the home, on the job, and at play. In some cases, rubber literally became the foundation of where we lived and worked. Albany Court was built in London above the St. James Underground rail station. It was the first building to rest on natural rubber anti-vibration mounts.
As far as some of the other extremes on vibration control for rubber, some of the applications that are in use today are for isolating buildings, where you would suspend or support the building on rubber mounts, and if an earthquake happened, then basically the earthquake will shake and it would isolate the building from falling down in the earthquake.
The elastic nature of the rubber allows the motion of the earth to move at a different rate than the building. Rubber mounts also dampen the motion felt on some bridges. Rubber is also found atop most commercial buildings. Hot molten rubber is brushed across roof surfaces to form a water-repellent protective barrier.
Rubber is used to seal things so that either air or liquid does not get in. The uses of rubber are as varied as the imagination. They're pretty much rubber components in almost everything that a person uses every day.
That includes hand tools, kitchen appliances, weather stripping around doors and windows, and sporting goods. Even trains and trucks rely on rubber cushions in their suspension systems to maintain stability under heavy loads. Often, cargo is wrapped in a rubberized film wrap as a strong, easy-to-use, and cost-effective way to protect freight during transportation.
Silicone rubber was huge in the medical industry because silicone rubber was virtually non-reactive in the human body. So silicone rubber is used to this day for all kinds of medical applications. If there's something that's implanted in you, it's encapsulated in silicone.
While silicone is usually medically safe, it's not always the best rubber for certain clinical applications. Some industry experts are hopeful about the prospect of using the latex that comes from a plant called Waiuli.
It turns out that Waiuli latex is considered to be hypoallergenic compared to Hevea latex. In the healthcare industry, there is a crisis due to allergic reactions to natural latex products, such as gloves. For example, a dental technician may not be able to use the latex gloves that are typically used because of a severe allergic reaction.
Waiuli may be a significant remedy for some medical situations, but it could play an even greater role as a major contributor to the world's natural rubber supply. An important benefit for the U.S. is that Waiuli is grown in the deserts of North America.
Waiuli is a very interesting plant. It's a small desert shrub that's native to West Texas and northern Mexico. It's a very unassuming looking plant. If you drove by it, you wouldn't even give it a second look. It's about 3 feet tall and resembles sagebrush. But what makes it an interesting plant is that it contains the same natural rubber as the tropical tree that grows in the Far East.
Waiuli is one of the many latex-bearing plants that was studied extensively as an alternative resource during the rubber shortage of World War II.
The Department of Defense leased land from farmers in 3 states in the Southwest to grow about 32,000 acres of Waiuli during the war. At the end of World War II, the Waiuli that was growing in the Southwest was plowed under. And that was pretty much the end of any major Waiuli effort for a number of years until the oil embargo in the 1970s. Policymakers in Washington decided that we needed to take another look at critical agriculture materials that we were import dependent on, and natural rubber was one of those materials.
The quality of the Waiuli latex is marketable, but the processing of the plant has yet to provide sufficient yields to make Waiuli a valuable commodity. But that's changing.
In Waiuli, the rubber latex is contained in individual cells, so you can't tap it. You have to harvest the entire shrub, grind it up, and extract the latex. Because of the economics, imported rubber has always been relatively inexpensive. But now, because of this hypoallergenic quality of the Waiuli latex, products can command the premium price to make it a commercial success.
The U.S. Department of Agriculture continues to research Waiuli as a domestically grown source of natural rubber.
I think it's here to stay. We're starting to realize that we need to be a little more diverse in our agricultural base as well as our industrial base. From an agricultural perspective, Waiuli offers an opportunity for a new crop beyond the conventional crops that we grow in this country. From an industrial-based perspective, we will have a domestic source of a critical and strategic material.
Alternate sources of latex will help to assure the development of new rubber products. But it's the old rubber products that have been difficult to inventory and destroy. Building contractors used 41 miles of butyl rubber to seal the joints of the Houston Astrodome. Rubber will return on Modern Marvels. Recycling tires back into tires is not a viable alternative.
The downside about rubber that's cured is that you can't remelt it and you can't reuse it. You have to grind it up to reuse it.
It's the vulcanization that gives rubber its form, which prevents it from being reduced to its prime elements again. In the 1970s, factories and kilns burned tires as an alternate fuel source.
And we were quite happy with tires as a fuel. If you substitute tires for coal, you end up with less sulfur dioxide emissions, less nitrogen oxide emissions.
At best, tires can be ground to a fine powder to be used as filler material in some applications.
Generally, you can use reground material, very finely reground material. For example, you use rubber in pavements today, roads. You can use rubber in artificial football fields, artificial soccer fields, also on tennis courts. There are many places where you can let the old material be used.
I should raise one other point, too, and a point that most people aren't aware of. In the last 20 years, we've probably increased the life of the average tire by more than 50%.
Tires with a lifetime warranty have become commonplace and may slow the rate of rubber entering the scrap inventories. This may also reduce the burden on the natural rubber plantations.
My understanding is that most of the good rubber-growing lands have been maxed out. There's room for growth in Indonesia. There's some room for expansion in Vietnam. There's room for expansion in China, and the Chinese are planting rubber like mad. But in general, you see a scenario where rubber production is not going to increase nearly as much as demand.
The business of growing rubber is always risky due to climatic and botanical conditions, especially the fungal leaf blight.
One of the curious things about the South American leaf blight is that it's not a problem until it happens. And we don't have a lot to go on to really ascertain what are the possible consequences of this disease breaking out in Southeast Asia. It's not as if the sky is going to fall in if the disease reaches Southeast Asia. I mean, it's a fungal parasite. It can be controlled with fungicides. The problem is that the big plantations may indeed have the resources to do so, but roughly 50% of the rubber production in a place like Malaysia is coming from small family farms that do not have that kind of infrastructural support.
Nevertheless, many experts are optimistic about the outlook for the rubber industry and are confident elastomers will remain poised at the leading edge of technology.
And in the future, we can hope to see a time when nobody will have to worry about having a flat tire.
And now that we've learned to deal with this new science, relatively new science called nanotechnology, the reinforcement of polymers with nanoparticles has led to a new generation of highly stiff, very lightweight materials that will go into the transportation industry and the aerospace industry.
I see continued evolution of the materials, continued development of new materials that will meet the new challenges.
Another thing that's being done is to add some kind of a controllable feature to the molecule of the rubber itself, where what you can do is actually make the rubber change shape if you put an electric field on, and essentially create something that's very much like an artificial muscle.
The prospect of making functional biomechanical tissue from rubber may give future candidates for reconstructive surgery a reason to smile.
There's always search for that significant technology that is going to be a leap rather than a evolution. I'm sure we'll have those. We've had them along the way. History says that we're going to have them again. I don't know what they'll be, but I'm sure we're going to pursue them.
Only time will tell how far rubber technology will evolve. In our homes, our industry, our science, and beyond, rubber will always be wedged into our existence. And we'll still need the white blood of the forest, sliced from the hevea tree bark and collected into tiny cups, just as it was 400 years ago.